So today we're going to dive into a lot of data structures. So this is going to be mostly a data structures class today, and talking about file systems because we're talking about implementation, and we're looking at a lot of the trade-offs that we can make in terms of actually structuring this file system, the underpinnings of that file system on an OS. So the first thing we're going to talk about is the implementation of directories. So there are a couple different ways we can implement a directory. The main options are either a linear list or a hash table that augments the linear list, or a hash table in general. So a list just contains the names of files and pointers to the data blocks for each file in the directory. So it might look something like this, where we have an array. So each array index is a pair of file name and block pointers. These each represent some file in the system and the pointer to the actual data for that file. So this allows the OS to quickly store each file name and each block pointer. The biggest issue that we have here is that for creating a new file, we have to search for an open index in the array. So let's say that index 3 doesn't currently have a file in it. If we want to create a new file, we have to find that index that is empty, and then we can add a file name and block pointer to that location. To delete files, we can either mark the directory entry as unused by assigning a special value, like having it blank, or we can use an extra bit to indicate unused directories. So we can have some extra metadata attached here to make this like a file name, block pointer, used, unused for each entry. We can also sort of compact things by having making it work so that, like, if we deleted entry 3, we would just move entry 4 into entry 3's old position. And in that way, we can sort of keep this as compact as possible. That also makes creating files a little easier, because then we can just create at the last index of the array all the time. So whatever the current size of this file list is, we can create at the end. The main issue we run into here is that all of these operations are going to require finding a file in this list. So we always sort of have to either find the open position, or find the file that we're going to delete, or find the file that we want to access. So any number of these things can, any number of these operations cause us to have to search this linear list for a file name, and then get the name and its associated block pointer to check whether we have the file. We have to maybe check when we create a file. We have to check that we have a file, or we don't have a file with the same name. When we delete a file, we want to make sure we do have that file name, and then delete its contents, or delete any links that it has. So we have to constantly be searching. So I have two questions, which is, what is the worst case asymptotic runtime for searching an array? And then what do we do to make searching faster, and is that transformation worth it? So go ahead and jump into your rooms and chat about this for a couple minutes, and I'll be in to answer questions and help out. Okay, so I think most of us got it eventually there. So the worst case is O of n, right? Because this is it is a list, and the worst case it is in the last position. So we have to look at everything to find what we're looking for. So then the question is, can we make this faster? And I think a lot of you figured out binary search can make searching O of log n instead, which is orders of magnitude better than O of n, but it requires a sorted directory. So we have to have a sorted list of things here. So I'm actually just going to edit this, and let's sort of just say that we have, you know, our things here, and I'm going to add some names in here for example. A second. So let's say this is a.txt, or this is, you know, file alpha beta Charlie, something like this. I'm not quite using my alphabet right there. So let's say we have these files. I have them in sorted order. So if I want to look up number, you know, I want to look up beta and see if I have the beta file, I look at this entry and I see that directory 2, or directory entry 2, is not the one that I want, but it is higher lexicographically than beta. So I'm looking for beta. I see something that starts with a C. That means that because this is sorted, I can look in the front half of the array. So I can look at alpha or beta next, and then determine if it has beta or not. So then I look at beta next, and I found the thing that I'm looking for. So this is the same number of steps as if we had done, you know, sort of linear search. But if I'm looking for zeta, then instead of being, you know, O of 5, I'm going to look at Charlie, Foxtrot, and then finally find zeta, and that's going to be less steps. And as this gets larger and larger, that gain in performance is going to be even larger because we're looking at log of n things instead of n things to find what we're looking for. The problem is now, let's say that I want to insert I want to insert something that is like BAAA. So I want to insert file. Now I want to insert BAAA into here. This is going to be lexicographically in between alpha and beta, right? So because it starts with a B and then has an A next, it is alphabetically before beta, alphabetically after alpha. And so I need to insert this into this list, which means that what I have to do is, one, find the position that I'm going to insert it in, which is here. And then I've got to copy all of these things and move them to later in the list. So I've got to move all of my other data back to the back. And I need to send some of these backwards. I seem to have lost stuff, but hopefully you get the point that, you know, then we would be able to insert these at the correct position into the list. But that requires copying a bunch of data from one place to another, taking a lot of extra time and effort. So essentially the gist here is that we need to make sure that it is actually worth it to move this stuff and keep a sorted directory instead of just having the worst case of searching for these items. So if we try to only use this single data structure, we can do some things. We could use a linked list instead, which then we wouldn't have the copying. We just have sort of pointer manipulation to insert that into the list, but we'd still have the overhead for sort of searching, finding the spot, making space, sort of maintaining this sorted order the entire time. So we need to know if more searching happens or more creation happens to know if maintaining sorted order is worth it. This is another one of these like it depends questions. So it's really just a matter of, is it going to be worth it for us to maintain sorted order to eliminate some of the search costs? And that's going to depend on sort of the metrics that we have for our system. How much are people searching for files? How much are they adding and deleting files? We also would probably have to, for deletions, compact. So when we delete something from one, we'd have to move, 2 over, or we'd have to have a linked list that has more pointer overhead, which we'll talk about a little more later, right? It has pointers to each directory entry. So then, for large numbers of files, we have a lot more overhead to maintain these pointers between entries. So there are a lot of trade-offs here in terms of the data structure that come into play because of the fact that we want to make some of these operations faster. So the sort of trick, the cheat way around this is if we have extra memory, we can increase the speed of finding something in the directory without using either a sorted directory or without having some sort of additional linked list pointers within there. But in general, we don't have to have the directory be sorted if we do this, and we can still find files quickly. So here what we do is we use a hash function, a hash table, and the hash table simply maps from the file name to the index in the array where that file name exists. So maybe this is better if we have an actual index here. So we have, file name is actually beef.txt, and in here is, ox something. There's some non-hex characters in there that I will fix in a second. 8 or something like that. Is that enough? Same one. Make this a little smaller. Something like that. So we have an address that is a pointer in here. And that address is mapping to some location in the directory entry. So we just have a pointer to a new entry. So this is pointing to this array index. And this basically tells us that this is index 4 in this array. We could theoretically also just store a 4 here instead of the pointer, and then that would give us an index into the array if we have the base address of the array as well. But this allows us a little more flexibility in that we could use a linked list to to represent it underneath, or a tree or something like that, if we do want to still maintain sorting but find this even faster. And the nice thing about this is that it allows us to very quickly find beef.txt in this directory. We don't have to have these be sorted. So, we can have flash.exe or something, and we can have, alpha.txt. We can have any sort of names in the files, and it doesn't matter because we have this hash table to accelerate finding the files in this directory system. We don't have to compact things because we don't necessarily have to have these entries right next to each other, and searching a hash table or finding a hash and then following this pointer is going to be O of 1 because of the fact that we can in fact just find the entry, follow it, and that leads us to the correct file in the directory system. It does have the standard issues with hash table collisions. So if we have two things in the file entries that sort of map to the same place in the hash table, we have to do the usual stuff like chaining to the next location or having a linked list of entries, which then makes it degrade to like not O of 1, but some sort of O of n for however many collisions we've had. So there are a number of things that can go wrong here, but in general, this will allow us to have O of 1 searching while still maintaining this very simple structure under the covers. So this is another option that we can take that allows us to search quickly through our files and find them very quickly and efficiently while still sort of maintaining the same simple underlying structure. Okay, so this is just kind of a classic optimization. I feel like I was asked something like this in like every interview I've had for an internship, where they give you some algorithms problem you solve that in a sort of inefficient way. And then they ask you like, well, how could we speed this up? And it's almost always like, oh, we can add a hash table on top of this, and that way it's faster to search for something. So this is a very common optimization that we just trade some amount of extra space for increasing our speed. So yeah, we're using more space because we now have this hash table that has some fixed size and stores pointers and possibly has linked lists added into it. So we're taking up a decent bit of space extra, but we are increasing our speed quite significantly, especially if we have large directories. So this is another sort of factor that we have to think about here is like, how many files do we have in these directories? Is O of n actually that bad? Or are we talking about like O of 10 in most cases? And I think a lot of folders on our systems are going to be pretty scarce. There aren't that many files in most folders. So maybe this n doesn't actually matter quite as much because it is a small number of files to search through. And even O of n is not going to take that long. But if we have very large directories, then it's going to be a bigger problem. Does that mean that the hash hex value is the pointer to the start of the file? Or is that number just associated with the file and you search the number in the directory? So the hash hex number is essentially the same as if we had here, that this is index 4. So the hash hex number is really just, we hash into this table. So hash ends up at, hash of beef is index 1 here. And hash of, let's add another one of these. We might have hash of alpha txt might be index 0 because that's where that is. And then we would have, the same sort of deal here where, it maps to the file system. But in this case, that one would go, point over to index 0 there. So it's really just mapping from the name of the file to the name of the file to the index in this directory entry. Yeah, we're trying to basically just map to that. So the address would be directly mapping to the address of that array. So we can either store the index itself. So store index itself, e.g. Hash of beef.txt equals 4. Or we can store a pointer to the index, e.g. hash of beef.txt equals ampersand directory at 4. So it's either we store the actual index, or we can store the address of the array for the directory at that index. So that's kind of what I had in the original example, where this is like, OX, whatever fake hex number we have, that's the address of directory entry at 4. Just making up a hex number here, but like, we'd have some things stored in memory. We'd have a memory address that's like 32 or 64 bits stored there. Or we can have an integer that then we use to say, okay, directory at 4 is beef.txt. But we basically just want to map from the name and use some, mathematical function to get to that index in the hash table. And then that tells us what index it's going to be there. Yeah, so depending on your file management, you may have larger file directories than not. Like your downloads folder may get ridiculously huge because you don't delete them very often. I know my personal management scheme for that is every once in a while creating a folder called backup and copying everything into that folder. Which is not the best way to do it, but it works kind of okay. So how do you handle collision prevention? Is that just dependent on your hashing algorithm? Yeah. So that is something I think worth thinking about here a little bit, because it is possible that we have file systems where you do have things like, okay, I'm going to create file 1.txt, file 2.txt, file 3.txt, file 4.txt. You might have things with similar names. And so you want to make sure that those things with similar names don't end up colliding at the same place in the hash table, and then making it so that you end up with the same sort of linear, having to look through entries in that hash table consistently. But there is no sort of generic way of like making sure that you don't have collisions. There are ways to increase or decrease the probability of collisions, mainly that you use a size that is a prime number. So prime numbers have nice properties in that, sort of every prime number will allow you to sort of map different numbers that are above that to, basically groups of numbers. So you have less likelihood that they map to the same place. Like if you have an even number, like I have a hash table of size 2, then every even number maps to one index, every odd number maps to a different index. If I use a prime number that's larger than 2, so a larger prime number, it's less likely that I'm going to have collisions based off of the numbers that are generated by my hash function. But otherwise, there's no sort of like fast method to decide like what the hash function should be. It's just kind of trial and error based off of the data. And generally, I think most of them are going to do okay if you follow that guideline of having a prime number be the size of your hash table, which unfortunately in this case is a little awkward because we're kind of trying to make things like power of 2 sized. But making things power of 2 sized is not always going to be the best in terms of making sure that things don't collide in that hash table. So we may want to have like power of 2 and then find the next closest thing, next closest prime number below that allows us to sort of fit the data properly and not have collisions. So yeah, there's no perfect method for doing that. So good questions. Keep them up. Okay, so that is the sort of data structures underlying these directories. The next thing we have to talk about is file allocation methods. So this is sort of looping back onto some of what we talked about with page allocation and memory allocation in general. So these are really similar problems. We're going to see a lot of the same stuff that we saw with memory allocation when we're looking at file allocation. There are some small differences, but for the most part, we have the same kind of issues. So our first approach here, just like we had for memory allocation, is to do contiguous allocation. So in this case, when we try to allocate a file onto the storage device, we simply map a contiguous region of blocks to each file. So we can see here the sort of grayed out parts are the files themselves. What our directory has is a listing of each file name, the block that it starts at, and the length of the file. So length is the total number of blocks we're using, and the start is just the start block. So we can see that like count here starts at 0, uses 2 blocks. It uses block 0 and 1. It has space that it could use 2, 3, 4, and 5 if we needed to as well. We have the file F, which starts at 6 and uses 2 blocks, so 6 and 7. The file TR that starts at 14 and uses 3 blocks, 14, 15, and 16, so on and so forth. So we just list how many blocks we're using and where they start. So this has similar problems to contiguous allocation in main memory. As we can see here, we can allocate files of size up to 4, up to 6, up to 2, and up to 3. If I want to allocate a file that needs length 7, right now I don't have any place that I can put this in our storage because we don't have a hole that is big enough to fit a 7 length. So we have to basically compact or do something else in order to make more space. So this is external fragmentation. This is just about the same as we saw in regular memory allocation. So another question for you to think about for a couple minutes here is what factors make dealing with external fragmentation in secondary storage more difficult than dealing with external fragmentation in main memory? So take a couple minutes. I'll be around to chat with you about that. Can you hear me on here? Okay. So yeah, I think those are both good ideas. I'm gonna move on to the next group and see what they say. Okay, what do we think? Yeah, so it's more persistent, right? Okay. I'm having Discord mic issues apparently, so and they're not fixing themselves quickly. So hopefully you can hear me here. Anyways, I think so. I heard a couple good things. So there are a couple big things here. So I heard that it's bigger. So secondary storage is larger. So things like compaction are going to be more difficult because we have to deal with a much larger amount of physical memory that we're compacting. So if we're trying to like find all of the stuff that we can sort of crush into one place, it's going to be more difficult. It's going to take a lot longer. So whereas like compaction in RAM tends to be like a maybe couple second process, at most, minutes, depending on, how thorough we're being about this. this is going to be like hours in secondary storage. So this has to be like an overnight process. If you ever like defragmented your hard drive, this used to be a thing. I don't know if any of you are old enough to have had to do this on your Windows computers, but this used to be a thing with like Windows XP especially, that I would have to like every couple months, run the defragmentation process and let it compact everything on my hard drive. It wouldn't do it by default because it was just too slow. So you sort of had to, yeah, I remember doing it on Windows 98. Yeah, you would have had to do it there too. So yeah, this was a thing that you had to do. And we have to think about the fact that 1, secondary memory is larger, 2, secondary memory is slower. Because it's larger, operations on it are going to be slower. So this is a, takes hours to compact. That's one thing. Another interesting point I thought came up was that RAM sort of defragments itself as soon as you shut your computer off because it is volatile. So secondary storage is non-volatile. So fragmentation is persistent. So if you have fragmentation, you shut off your computer, your secondary storage is still fragmented. Your memory is no longer fragmented because you've shut it down and processes are no longer running. So sort of an interesting point as well. So that's the first problem, is that we have external fragmentation, just like we would for dynamic allocation. The second problem is that we just don't know how big to make these files. So right here, we have enough room for count to grow by 4 more blocks. We have enough room for F to grow by 6 more blocks. We have enough room for TR to grow by 2 more blocks. We have enough room for mail to grow by 3 more blocks, and no room for list to grow. So when we allocate a file, we just really don't know how big it's supposed to be. With a dynamic allocation, we allocate these with like malloc, right? And malloc says, how many bytes do you want? So we say malloc, or we say our void star pointer equals malloc number of bytes. So that tells us when we allocate a dynamic allocation, this tells us that this is actually going to be a particular size. When we open a file, we just say, file star f equals f open name.txt. And then we say read write or something like that to tell us what permissions we want on that file. Nowhere here does this say the size. So if I'm creating a new file with this, the programmer is not telling the OS how big that file needs to be. And this would be a difficult question for you to answer as a programmer, right? You may not know how big your file is going to be on disk. And so because of the sort of difference between these two APIs, we don't know how big the file is going to be. And just in general, I think as a programmer, you can't be expected to know how big a file is going to be. So we have to sort of guess at how big a file could be, which generally we might say that it's going to be at least a block of memory. But if we allocate too little space, we may not have enough space for the required size of the file. If we allocate too much space, then we have internal fragmentation. So we have the same issue that we have with dynamic allocation, where if we allocate memory in pages, if we don't use a page of memory, then we have way less left over. So the way that we can solve this, or one way we can solve this, is to use what are called extents, which are essentially just pointers to another contiguous allocation. So here, if we needed to allocate more size for list, we might, end up basically putting a new part of list. We could insert a, can I insert a shape on here without making a new drawing? I don't know if I can here. But let's say we needed more room for list. We can't insert it right after there. So we could insert it at blocks like 2, 3, 4, 5. And then basically make the pointer go from 31 up to 2. And that way we have 2 contiguous allocations for this. And we don't have additional space being used. Or we don't have too much additional space being used for pointers. We just have the single pointer going up to there. If we need more space, we can point to the other open blocks, but we can make this larger without sort of having to have it all be completely contiguous. And this gives us kind of the best of both worlds to some extent, because it allows us to add space to our file, but to sort of minimize the pointer overhead, and to make it so that we can still quickly find a part of a file that we're looking for, because we don't have to follow too many pointers to get there. So to finish up then, sort of further expanding on the extent idea is linked allocation. So linked allocation solves external fragmentation and file sizing by just using blocks as a single block with a link to the next block. So here now we have a single file called Jeep. It starts at 9. 9 has a pointer to 13, which then has a pointer to 17, or has, I guess, just 9 points to 17, or 16. 16 points to 1, 1 points to 10, and that's the file. So, or 10 points to 25, and that's where it ends. So we have a pointer to the start of the file. We have a pointer to the end of the file. We have no idea how many blocks are in between there in our directory listing. So this means that because we're just allocating blocks, we don't have external fragmentation. We still do have internal fragmentation, of course, because if we allocate it sizes of blocks, a file may not actually use that entire block. And we have sort of, we have the ability to size files as large as we need to, as long as we don't run out of all the space on the storage, because we can just continue in linking in new blocks into that file. We can use as many as we need. So there are 3 main downsides to this. Those 3 downsides are: 1, direct access is not cheap. So if I say I want to read at position, whatever, 2352 from read Jeep at position 2352. It's hard to find position 2352 in file Jeep because we don't know necessarily where the next file is that has that. So, maybe, or I guess this, could probably be a larger number. So let's say we have like 4 KB sized files. We're going to have to follow a number of these links to get to there. So basically what I'm going to have to do is start at 9, read 4 KB, or check to see if like this is big enough to have fit this address in the file or this byte of the file. It's not, so then I follow the link to 16, follow the link to 1, follow the link to 10, basically keep adding 4096 each time, eventually get to the final link there that tells me, maybe this is out of the file or that this is the place that I find that data. So let's make this 20,000 actually, because I think that means it fits. But it's hard to find that position because I have to follow all of these links to get to that position in the file. And there's no way for me to sort of say, okay, jump to that last spot. I can jump to the end block, but I can only do that. I basically have to jump to either the start or the end and then find the location within the file from there. So it's hard to actually get to that position within the file. And we'll pick up there on Wednesday. I think we'll be able to finish the rest of this and then maybe do softs on Wednesday. So I will see you then.